Okay, you're going to need to have your periodic table out because you're going to use it a lot today. So we're going to finish this chapter. And the first thing that comes up is a little bit of history. You need to know 2 historical names. Okay, and the first is right here. Okay, Dmitri Mendeleev is credited with creating the first organization of elements into some kind of a table. Okay? And the way that the first periodic table, his periodic table was organized, okay, was in order of increasing atomic mass. Okay, so today's periodic table has been altered a bit. Here is the guy, Henry Moseley. He is credited with putting today's periodic table in order. And today's periodic table is in order of what? Increasing atomic number. Exactly. Number of protons. Okay? Oh, this is good times, everybody. Do you remember electron configuration? 1s2, 2s2, 2p6, 3s2. You either love it or you hate it. Okay? Now, let me say something. The periodic table that is in your possession, ladies and gentlemen, is your personal periodic table. In Chem 1 here at Oakton, most of our teachers, we like to color code our periodic tables in Chem 1. If that's helpful for you, go for it. Okay? We color them based on the sublevels, S, P, D, F. You are welcome to color code yours if you wish. Okay? You can write all over it. It's yours. Now, obviously, the ones we use on test days will not be. All right? But we're going to review this very, very quickly because you definitely did this in Chem 1. There are a few things that I am going to write on here that you might find helpful. You might not immediately remember why I'm going to be doing this, but you will in just a few minutes. Okay? For example, at this junction right there, I'm going to write some numbers. I'm going to write the number... Oops, wrong color. I'm going to write the number 3, 4, 5, 6, like that. And if you don't remember why I might be doing that, you will in a few minutes. Over here, at this junction, I'm going to write a set of numbers as well. 4, 5, 6, and then down here at the bottom, 4, 5. Okay. Again, if you don't remember why I'm doing that, you will hopefully in just a moment. All right, so let's review a little vocabulary before we even start into talking about electron configuration. Okay? That's what electron configurations look like. Sometimes you'll see electron configurations actually drawn out, where an arrow represents the electrons. That's called orbital notation. Let's review a little vocabulary, okay? Let's say you're looking at nitrogen's electron configuration right here. Do you guys remember, what do the big numbers in front, what do they represent? Do you remember? Energy levels, yeah. Okay, so I'm going to say big number represents an energy level. Okay, what do we call the letters? S, P, D, F, what are those? Sublevels, okay. right, now the next level underneath that is something a word I used over here. What when you draw out the arrows for electrons? Orbital. Okay, each box is representing an orbital. And then at the lowest level, what does each arrow represent? An electron. Yeah. Okay. So we've got some vocabulary here, and I'll kind of weave in some practice with these words as we go through today. All right, but let's just practice. Let's see what you remember, or don't. All right. Let's use the element as an example. Let's use the element cobalt. Find it. Put your finger on it. Okay, you guys tell me. If I asked you to write the electron configuration for cobalt, how's it going to start? How do we go? All right, 1s2, 2s2, 2p6, then what? 3s2. I'm hearing some very strange things coming from this side of the room. 3s2, then what? 3 what? Okay. Then what? Be careful. 3d7. Okay? Now guys, that is why I had us write those big numbers. And again, if you don't remember what those numbers represent or why we for some reason go from 4 to 3, we'll get to that, I promise. I will explain it. Okay? But that's what cobalt's electron configuration would look like. Right? What if, keep moving your eyes to the right, what if we were not looking at cobalt, but we're instead looking at bromine? 4s2, 3d, then what? 3d10, then what? 4p5. Okay. All right. So if that does not ring a bell to you and you don't remember that, then it's kind of on you to go back and review that. Okay. Do you all remember that there is a shorter way to write these out, like a shortcut, kind of? It's called the noble gas configuration. All right. So let's say we're doing that for bromine. Go backwards on your periodic table. What's the noble gas that comes before bromine? Argon. Okay, we put it in brackets like this. And that's to represent, like, okay, we've written the configuration all the way through argon, and then where do we go? We pick up from there. What would be next? 4s2, then what? 3d10, 4p5. Now here's the good news. On the AP exam, you are permitted / required, actually, to always use the shortcut. Okay? They are never going to ask, nor will I, ask you to write out the entire thing. I mean, bromine, that wasn't too bad, but can you imagine if I had you do, like, lead? Okay, that would take a long time to write that all out. So you are permitted to always use that shortcut. In fact, you are required to use that shortcut. All right? So, let's do some practice. Let's see what you remember. Okay. Okay, so guys, this is sort of the basic level of your electron configurations. If you took honors, you may have done configurations for ions, and that's the next thing we're going to look at here. But before we do that, we need to make sure that you understand the difference, that you remember the difference between a valence electron and a core electron, okay? Let's use the element iron as our example. Find iron, put your finger on it. Okay, everybody all together, like we're chanting in some kind of religious cult. Tell me, please, what is the noble gas configuration for iron? How does it start?
AR.
All right, AR in brackets, and then from there,
4 S 2.
then what?
3 C to the 6.
3D what? Thank you. Okay. Great. Now, valence, ladies and gentlemen, your valence energy level means the energy level that is outermost, okay? The one that has electrons on it that is furthest away from the nucleus. Which one is that for iron? Is that energy level 4 or 3? 4. Okay. So whichever is the highest number. Okay. So for iron, as our example, iron's valence energy level is energy level number 4. Please tell me how many electrons are sitting on iron's energy level 4. 2. Okay. So guess what? Iron has 2 valence electrons. Look down at your periodic table. How many total electrons does iron have? 26. What's 26 minus 2? 24. Iron has 24 core electrons, ones that are inside that valence level. Okay? And just to review from Chem 1, just to make sure, guys, any element in group 1 has how many valence electrons? 1. How about group 2? 2. Your transition metals, like iron, most of them have 2, some of them have 1. Well, I'm not going to get into that, don't worry about it. What about elements in boron's family? 3, 5, 6, 7, 8. Okay, so 8 is the greatest number of valence electrons you can have. Okay, now let me just give you a little bit of a sneak preview of something that I will explain in more detail later. But in Chem 1, when we first teach electron configuration, a lot of my Chem 1 students always have trouble understanding why is it, if this is the outermost energy level, why do we write that one before that one? Or why is it organized that way on here? Well, guys, just a sneak preview. I will explain in more detail later. Electron configurations are written in order. The sublevels are written in order of increasing energy. Okay? 4s, even though it's outermost, 4s is written before 3d because it is at a slightly lower energy content. I will explain in more detail later on. Okay, let's use iron again. Iron had this configuration. 4s2, 3d6, is that right? 1, 2, 3, 4, yeah. Okay. What if, instead of writing the electron configuration for a neutral element, okay, what if I asked you to write it for an ion, okay? Now, first things first. I don't even care what this number is. Tell me, please, when an ion takes on a positive charge of some kind, what happened? How did it get that way? Yeah, it lost electrons. In this case, it lost 3. Okay. Well, let's read this statement up here. It says electrons are removed or added to the valence energy level first. Which one of these was the valence level? 4. I need to take away 3 electrons. Where am I going to pull them from first? I'm going to pull them from 4s. I'm going to pull both of those electrons. Gone. But I still need to take one more. And look what it says. If needed, and only then, once you've taken away from the valence level, only then can electrons be removed from the D sublevel. So this isn't going to be 6 anymore, it's going to be 5. So let me clean this up a little bit. This is what the electron configuration for iron with a +3 charge will look like. There you go. My suggestion, if you're feeling a little bit shaky on this, when writing configurations for ions, my suggestion would be write out the configuration for the neutral element first, and then figure out where are you going to go from there. Let's do one more example. Instead of a cation, let's do an anion. Let's do sulfur, pure sulfur. Tell me please, let's chant it together. What would the configuration for pure sulfur look like? Okay, Ne, then what? 3s2, then what? 3p4, okay. Well, what if I had sulfur in its ion form? What does a -2 charge mean? What happened? It gained 2 electrons. Okay. Well, it says electrons are added to the valence energy level first. Okay. Energy level 3 is my valence energy level. Can I put these 2 electrons in 3s? Why not? It's already full. S can only hold 2 electrons, so where do you think I have to put them? In P. Okay, so let's do that. Now, doing this, ladies and gentlemen, what noble gas has that gotten me to? Argon. Okay, guys, you can't just put the letters AR in brackets and have that as your answer. You can't do that. You have to write it all out. What if, though, I should have said this on the previous slide, what if you are asked, forget about an ion, what if you're just asked to write the noble gas configuration for krypton? Do you think it's okay to just put KR in brackets? No. You've got to back up to the one before it. Sorry. Don't shoot the messenger. Okay. All right. Let's do some practice. Go get them. Okay, check your answers. Now, with these answers up here, let me say something to you that some of you might be wondering, maybe not. Okay. On our next test, on the AP exam, could you be given an ion and they ask you to write the configuration? Absolutely. Could we ask you to go the other way? Look at this configuration. What ion has that configuration? Could I ask you that? No and yes. Here's the thing. Do you notice that this ion and this ion all have the same configuration. So could I give this to you and say, well, what ion is that? Not really, because it could be multiple different ions. So let me be clear. Could I ask you that in free response? No. Could I ask you that question in multiple choice where you only have certain ions to choose from? Yes, I could. All right? But I can't just give this to you blind and say, well, what ion is that? Because it could be any number of ions. All right, so ladies and gentlemen, let's talk about, there are rules. There are rules that dictate where electrons end up, where they situate themselves on these energy levels. And the first rule is the Aufbau Principle. Focus on this second statement right here. Okay. The Aufbau Principle essentially says electrons fill in energy levels closest to the nucleus first, and then as those fill up, then they move further out, away from the nucleus. Electrons fill in low energy orbitals. That means orbitals closest to the nucleus, those fill up first, and then electrons progressively fill in to higher and higher orbitals, which just means moving further and further away from the nucleus. Okay? I'm going to show you a diagram on the next slide that you may have seen before, and you certainly do not need to copy down or memorize, and I'll explain why. Okay? Some of you may have seen this before. Maybe you haven't, maybe you have. Okay? What we have here are all the different sublevels. And do you remember, what do the boxes represent? Orbitals, okay? All the different sublevels and orbitals all across the periodic table. And look what's on the y-axis. Increasing energy. What I'm trying to show you here is the 1s sublevel, the very first one we come to, is the lowest in energy content. What's next? Let's move, we're moving up the y-axis. What's next? 2s is the next highest in energy, then 2p is a little higher, then 3s, then 3p. It's hard to see this, but can you all see that 4s is slightly lower than 3d? Can you see that? Guys, that is why when you write out electron configurations, why 4s is written before 3d, because 4s is at a slightly lower energy content than 3d. Okay. And what comes right after 3d? 4p. If you are concerned with how am I going to remember that order, guys, I'm not sure you appreciate the work of art that this is. Your periodic table, as we read in English from left to right, top to bottom, is already in this order perfectly. You don't have to memorize it. It's already in that order. This is a work of art, everyone. You should take it home and frame it when you're finished with this course. Okay? Now, first of all, because somebody thought I was trying to say something else, I'm meaning this to represent the element helium, not he with 2 electrons shall blah blah. No. Okay? That's not what I mean. Helium that has 2 electrons situate themselves as low in energy as possible. This would be a violation of the Aufbau principle if I did this. If they're not there, they're not in 1s, but for some reason, I put them up there. That would be a violation of the Aufbau Principle. Now let me show you one other thing. I want to see how well you were paying attention last class. What if just that electron, just that second one, is not in 1s, but it's up here? That's not a violation of the Aufbau Principle. Do you know what situation this is? What did we call it last class? Yes.
Excited.
This is an electron in excited state. Okay? And let's review even further. How does that happen? How does an electron get from here to there? What has to happen? It absorbs energy. Can it stay up there for very long? No. So it will fall back to, what's it called when it's back in its normal place? Ground state. And guys, when an electron falls and releases energy, what do our eyes see? Colored light. Yeah. Okay, good. So you were listening. Very good. All right. Yes, sir.
Could it jump to like P or Q?
Sure. Yeah, you could take that electron and it could jump anywhere. It could jump to 4D, 6P, it could jump anywhere. It depends on how much energy it absorbed. Okay. So the Aufbau Principle is our first rule. Our second rule that should be familiar. Hund's rule. You can either use the formal definition or you can use my definition that's much more simplified. Every electron wants its own orbital before they have to start sharing, before they have to start bunking up. And let's use, find my marker, here it is. Let's use nitrogen as an example of this. Tell me, please, how many valence electrons does nitrogen have? No. Nitrogen does not have 7. 5. Thank you. Okay, I'm going to draw them out in that orbital notation. Okay, you guys tell me, please, the first 2 valence electrons for nitrogen. Make sure you got that. The first 2 valence electrons for nitrogen, what sublevel are they in? Two, not 2p, 2s, thank you. The next 3 are in 2p, and watch how I draw them. This is the essence of Hund's rule right here. Up, up, up. Every electron wants its own orbital, that's what these lines represent, before they have to start sharing. For those of you that have siblings, I don't think I have to explain this to you. Okay? We all want our own space. We are a selfish society. If we have the option to take our own space, we're going to take it. We do not like to share. This would be a violation of Hund's rule. That's not going to happen. Electrons just don't do that. Humans don't do that. Guys, here's your third rule. And ladies and gentlemen, this rule can be summed up just with this picture right here. Hush. Pauli Exclusion Principle. First of all, there's 2 parts to it. First says an orbital, just like I drew on the board. These lines represent an orbital. An orbital can only hold a maximum of 2 electrons. It can't hold 3. It can't hold 4. The other part of the Pauli Exclusion Principle is that these electrons, the reason we draw up and down is because they are in opposite spin. Now, you're going to have to stretch your brains a little bit here, because I want you to imagine what an electron is experiencing. Electrons are rotating around their own axis, revolving around the nucleus, and do they travel in just nice pretty circles? How do they travel? In waves. Okay, good luck trying to demonstrate that, especially when you think of two electrons. When I say they are in opposite spin, I mean if one is spinning clockwise, the other is spinning counterclockwise, and revolving, and moving in a wave. I'm not demonstrating that, I can't. It's too much. Right? So, those are your rules. Okay, one other thing that you need to be able to recognize, you would never be asked to draw this, okay, but you need to be aware that each sublevel has a unique shape. S sublevels, doesn't matter if it's 1S, 3S, 6S, it doesn't matter. They are spherical in shape. So the S sublevels are spherical. This is what a P sublevel looks like. Can you guys tell me, why does this slide have 3 pictures when the previous slide only had 1? What is it that an S sublevel only has 1 of, that a P sublevel has 3 of? Orbitals. All S sublevels have just 1 orbital. P sublevels have 3. How many electrons can fit in 1 orbital? 2. So 2, 4, 6 total electrons. Here's what D looks like. Things start to get really funky here. That's what D looks like. Please don't ask me why the 5th orbital looks different than the others. I have no idea. Okay? Are you ready for F? It's the weirdest of all. You're not going to have to draw these. Do not worry. Here's F. What? Okay. Guys, this is getting into that quantum physics business I was talking about. I have no idea what's going on here. All right. But the take-home message here, guys, your periodic table is a work of art. It is organized perfectly. If you think about it, take, let's say, your halogens right here. Think about how the electron configurations for all of your halogens end. They all end with some number P5. Do you agree? Okay. Because elements in the same columns, because their configurations end the same way, that means that they're going to have very similar physical and chemical properties. That is the beauty that is the organization here. Okay? And the last thing, just a little bit of vocabulary. You guys know where your transition elements or your transition metals are. If you ever see the term representative elements, that just means elements in the S and P area. This one you don't have to memorize because it's written on your periodic table. That's down in the F sublevel. It's just names for these different areas. Okay? And ladies and gentlemen, that is it.